Okay, so welcome. And especially let me know if I speak too quickly. So I've been who I am. Yes, sorry, I will talk about opcodes and a little bit about the PE file formats and their oddities. So I've been a reverse engineer for some years, for some time. Also, I created a project called Corkami. And I also, in the past, I worked on the MAME, the arcade emulator. And professionally, I'm a malware analyst, but this is only on my the behalf of my hobbies. This is just my own experiments and research at home. So I'll introduce Corkami. Corkami is just the project, the name of the project I created for. It's a RC-oriented project. I try to keep it directly to the technical stuff. No ads, no download, no login required, and really direct the good stuff. And I try to update and make it useful, so I also created the cheat sheets and the kind of easy document that I would use myself for the work on a daily basis. But it's only hobby. I do that once the kids are asleep and until late at night, so it probably doesn't look professional and as good as I would like to be. So right now, the Corkami, the form of Corkami is wiki pages and cheat sheets, and I focus on the creating as many as possible relevant proof of concepts. So the binaries are handwritten. Usually I don't use a compiler. I created the P myself so that it's only focusing on the exact interesting point and you don't have a lot of noise. Even you don't probably need to IDA to actually understand what's going on, because I try to focus only what's important. The binaries are all directly available to download, so you can really test your debugger, your tool, your knowledge, or just get them directly from that. So far I focused on the PDF assembly and the PE file format, a few other stuff, but that's mainly the most covered subject of my website. And I also share that with the very permissive license, so BSD, you can reuse them commercially, whatever. Even the images are done in an open source format. So the story behind this presentation is that some time ago I was young and innocent, and I thought that CPU being electronics and whatever, it had to be perfectly logic and no problem. Then I was tricked by malware, and basically IDA wasn't able to work on it. So I decided to go back to the basics and study assembly and PE files from scratch. I created in the meantime documents on Corkami, as I said, and now I'm presenting you more or less the final result, or the good programs result. If I was just a guy who learned assembly, and I probably wouldn't be in Hash Days to talk about it if I didn't get a few achievements from various tools. So basically, I failed all the disassemblers that I tried, and I also created a few crashes in IDA. So now, I insist that all the authors were notified, and most of the bugs are already fixed. But so basically it was like this in 6.1, you get a direct crash, but now it's fixed in 6.2 and everything. And Hue, that's the latest version, but the newest unreleased, well, the newest beta fixed that and so on. So the agenda for the presentation is that I first try with an easy introduction, but I assume that most of you already are familiar with disassembly, right? Or yes. And another question, are you all familiar with or you already had an event of undocumented disassembly in your, or never? Like you trust IDA and that's all? For you, is it a common thing to have undocumented disassembly in IDA? Raise your arm. Who? No? Okay, not so much. Okay, and then after the introduction that will go on quickly, I will mention a few tricks, then introduce the the program that I created, and I will also talk a little bit more about the PE file format. So as you all have assembly knowledge, I will go quickly on that. So basically, you compile a binary, there is assembly. There is some there is some common points between the code and the assembled code. Then, of course, there is a relation between the opcode and the code. So by now, you all know that. So what's important is that the assembly is generated by the compiler. But actually, what is then from the assembly, what is the only kept in the binary are the opcodes itself, which are understood directly by the CPU, which means the CPU just knows what to do with the bytes. It doesn't care if you or you don't or the tool you're using knows what it will do, because it just does it. And the problem is that what we read is not usually the opcodes for most people, but actually the disassembly. And if the disassembly doesn't give you, the disassembler doesn't give you any result, well, we're stuck, we're blind, we don't know what execution what the execution will do. And the other problem is that because of opcode length, you don't even know what the next instruction will be, because you don't know how to disassemble it. So here I'll just create a few one undocumented opcode in the simple program. So basically, we just emit I'd say keyword in that's a Visual Studio 2010 Ultimate. You will get a byte that is unidentified at disassembly. So you get the first you get question marks. So basically, that's this program, even though it costs several thousand of dollars, is not able to, doesn't know what to happen. So usually if you do that, if you check the Intel documentation, there's nothing to see at the D6 opcode. So there's nothing to see there. Microsoft doesn't say anything. Intel doesn't say anything. So usually if you try that, you could expect bad results. So not documented directly, usually it's a crash or not the expected results. But here, in this case, the specific case, no problem. We don't know what it was. If we follow Intel or Microsoft documentation, we don't know what happened. But if the CPU just does its stuff. So what happened is that actually D6 is a very simple opcode that doesn't do much, but somehow it's not documented by Intel because it's documented by AMD. And most of the opcodes are actually documented by AMD, but not Intel. I don't know why. Anyone has an idea why? It's quite a trivial opcode, but it's not. Intel still says there's nothing there. Okay, so it's commonly used. The common use for those undocumented opcodes are malware and packers, just to prevent automated analysis or easy reverse engineering. What's funny is that Intel, if you follow the documentation, you will have many holes, but Intel's own disassembler, Z, which is free of use, it's not open source, but just handle all these opcodes correctly, while Microsoft and Visual Studio and WinDBG, they follow blindly the documentation, and so they will you will get question marks, even though Intel perfectly knows what it does. So it's like Intel, it's more like do what I disassemble and not do as I disassemble and don't read my documentation. So of course you could argue that WinDBG is only made to debug what the compiler, Microsoft compiler, created, but then it kind of rules out WinDBG as a malware debugging tool, because you just insert a D6. I mean, it's trivial, and the WinDBG is just not able to tell you what the instructions are, so it's not very useful for a malware analysis tool, for a malware analysis debugger. So another problem that happens is that, of course, each of the undocumented facts are available. Maybe one you will have in a Trojan, one in a Packer and everything, but it's not so easy to find a good and exhaustive, clean test set to actually gather all these undocumented facts. So, for example, if someone say, a colleague mentions undocumented opcode or behavior, and then you say, oh yeah, it's in mebroot, so you skip this part of the file or whatever, and then you're actually, first it's a malware, so you cannot really spread that, and then there is a lot of noise, the malware payload or something before and after, so it's not so easy to analyze. So that's why I focused on creating a small and clean test set that would actually provide insist just on one particular instruction or fact. So now let's start at last the real stuff and a few of the undocumented opcodes. But before I actually started wondering what's the actual possibilities of the CPUs, I didn't even know what are the possibilities, what are the opcodes that are still supported or not by the CPU. And I think it's a bit like English. Everybody or most people in the world would be able to read and understand these words. And if you see some disassembly, well, you're used to see all these opcodes. They are made by all the compilers, and they are so common that if they are not here, we are a bit ill at ease, and if it's something different, then we probably be surprised. So this is a standard English, but the Intel CPUs being were made in the 70s. In the 70s, sorry. It's a bit the same as if you take that's Shakespeare English. So you could say it's still English, but you know, I don't know what that means actually, or maybe I forgot. I quickly forgot at least. And it's a bit the same for those opcodes, which are still supported by all the CPUs that we have, all the Intel CPUs, but we probably don't know what they actually do. And that's a problem. I actually made one of the proof of concept I made is only using these old opcodes, and these opcodes are actually doing something. So if someone is familiar with reading that, maybe I should ask, how old are you? Because myself, I'm used to the push jump calls, but when it's about this, what is exactly being done? And it's still working on an i7, and it's still usable by malware, packers, or anything, and yet some of them are unused, totally unused now, and they are still fully working on modern CPUs. And of course, it's a bit like English. It's an evolving language, and a bit like maybe the oldest generation of people, of human, wouldn't be used to the buzzwords, the latest buzzwords. These opcodes are sometimes present in the most recent CPUs. So, and you have direct opcodes for CRC32 or AES decryption, string matching, and then some complex operation in just one opcode. So this is possible. This exists in modern CPUs, not all of them, of course. One thing that I like is the move big endian opcode, because move big endian is the rejected offspring. It's only implemented in Atom CPU, which means this netbook supports this opcode, and the i7 64-bit doesn't have this opcode, even though it will have CRC32 or maybe AES code. So much for complete backward compatibility. There is no physical CPU, as far as I know, that can that can execute CRC32 and move big endian. And of course, move big endian is quite meaningless itself, because you already have an opcode for the for the endianness swapping. So I don't know. This small computer has an opcode that most PC don't. Okay, why? I don't know. If you know.
Is this opcode documented in the CPU feature set?
Yeah. Yeah, it's totally, this MoveB is totally documented, it's official.
But no, is it like a CPU-like physical construction, or is it implicit by this is a CPU?
Oh yeah, I don't know. I checked the value by CPU ID, but I don't know if it's relevant to the, but I think it's by itself, the opcode server. But the CPU ID result is so big that I don't remember it all. Another thing, a bit specific to Windows in my case, because I focus on malwares, is that before you do actually any opcode, I was focusing on what are the register values. I was also focusing on what are the register values when you start a program. And I found out that the register values by default when you start a program and you haven't executed theoretically any opcode, actually gives you some information that are actively used in malwares. So for example, at the start point, EAX gives you either gives you if it's older generation, XP or before, or Vista or later. This is not so used in malwares. I don't recall seeing it, but GS, if GS is null, then it's a 32-bit system, and if it's not, it's a 64-bit system. I will actually use that later in one of the tricks. And also the relations between the registers, there are many registers on the Intel CPUs, is not sometimes very clear. I was surprised that when you do a FPU operation, it changed the FPU status, the FPU registers themselves, but also the MMX registers. And somehow all the documentation I saw on the internet are always mapping ST0 and MM0 in front of each other, which makes sense. But actually, if you do just a single FPU operation, it will actually modify not MM0 but MM7. So if you do an FPU operation like load pi, and then you check the value of MM7, that could be used as a trick, or it's just like the way it is, unlike all documentation, Wikipedia and so on, that I could find about the overlapping of the registers. Another thing is that it was used as an anti-emulation trick in XP, that FPU also change CR0s, so you can have quite an unexpected anti-emulation trick by just using FPU operation. So here is it. basically, SMS store machine status word is an old 286 CP opcode mnemonic that was created at the 286 era, so before the protected mode was fully created. And so it allows you to access, to read the value of CR0s, even from user mode, while the move CR0 is actually a privileged opcode. For some reason, the higher word of the register is undefined officially by the documentation. So Intel just says, this is the value, the lowest value is correct, but you cannot expect the real value. So for some reason, I don't know why they say that, because it's actually the value, the higher bits of CR0s. And under XP, when you do a FPU operation, the value of CR0s will be modified and eventually reverts by itself. So you can have, just by, you do a store machine status word, and then you expect the result. Then you do FPU operation, then the result should be different. And then eventually, the result will revert to the original value. So it's quite a tricky and unexpected anti-emulator. You have a similar trick on 32-bit Windows, where GS is not stored in the context. So it means that on thread switch, the value of GS is lost, which means if you just wait for something, GS will eventually reset to 0. So if you set GS and you're just stepping manually, this is slow and this creates a thread switch, so instantly GS is lost. And also, like the previous trick, if you just wait for GS not to be, if you just loop until GS is not 0, this on a real system will eventually exit of the loop. But the first time it blew me, I was wondering what can happen there. There's no other thread. And of course, in my proof of concept, it directly starts like this. What happens? GS. So what should happen now? But on a real system, eventually it's it's reset to 0. And another thing is that, of course, it's reset to 0, but not in a 0 time. So if you do wait for GS is reset and then another loop, this can only happen between two reset thread switch, which means it should take a minimum of time, so you can use that for timing, anti-emulation timing tricks. Of course, I was also thinking that NOP is perfect because NOP is just NOP and does nothing. But originally, NOP is exchange AX with AX or EX with AX. But the problem is that, so NOP 90 is always doing nothing, but on 64-bit, you have another encoding to actually do exchange EX, which this time again doesn't do anything in 32-bit, but like all the other opcodes of in 64-bit mode, it actually resets the higher D word. So you have an exchange EX that does something, even though at first it looks like it would do nothing, but hopefully NOP, in this case the 90 NOP, is still doing nothing. And this is probably now common in malwares and stuff. Hint NOP was the multi-byte word, multi-byte NOP that actually gives a hint about what would be executed next by the CPU. Whatever the address here, it wouldn't trigger an exception. But as you can see, it's really a multi-byte. It can be a very long NOP. That's weird to say. Another thing is, once again, it's partially undocumented by Intel. So actually, the full range of hint NOP encoding are bigger on IMD documentation. And another thing is that because it's multi-byte opcode, if you, at the end of a page, if you insert those bytes and then it will look for the operands, then it could trigger an exception. So it's a NOP that could trigger an exception if at the end of the page. So yeah, thank you, Intel or whatever, I don't know, not sure. Move, once again, I thought move, being move, should be perfectly logic. Sadly not. So first, so all this is documented, but it's tricky because there were even bugs for that in all the disassemblers, I think. Well, except Z maybe. When you cannot do a CR0 move on CR0 or from CR0 on memory. So the documentation says that the baud RM is ignored. It doesn't mean it's illegal, it's just ignored. So if you do this, which could lead to a crash, it's actually interpreted by that. And you, as far as I can remember, you would fail all disassemblers with that until recently. Move A6D, a 64-bit opcode, is sign extending. So theoretically, it should work on from a smaller register to a bigger register. But if you use no rex prefix, which is discouraged, you can actually make it work like a standard move. And the other way around, move from a selector to 32-bit registers actually works. So many disassemblers were disassembling that at move AXCS because that would make the both operand the same size. But actually the upper word of the target register is undefined, but actually there's no funny thing here, there's no random value, it's zeros. So basically it makes it equivalent to move ZX EAXCS. VSwap is one of my favorites because I think it's like an administration. It's supposed just to swap the indianness of the registers, but because of various reasons, because of other reasons, external reasons, it's never really doing the work you expect. So only in 64-bit, it's actually correctly swapping the indianness as you would expect. On EAX on 64 bits, like all the other 32-bit opcodes, it will actually register the higher the word. Okay, and on Word, it's actually undefined again, but it's commonly used in malwares and packers because it just resets the. So it's like XOR AX. With this result, unexplainable result, I understand that Intel probably doesn't want to explain or just say it's undefined because we would be too ashamed to actually explain why we get this funny result. So BSwap is BSwap AX is also wrongly disassembled as by WinDBG and so on. So you think it would adjust it will be disassembled as BSwap EAX, and actually you clear the register. Can everybody understand this code? Anybody see the potential trap? So it pushes the address of next on the stack, then return takes the address from the stack, and so basically you just jump to an immediate value. And here, no. Sorry?
Execution ordering?
Yeah, it starts here. The execution starts here. Oh no, okay. It's not the point here. So, and of course, if you this is only debug 1, so it's been fixed in only debug 2. But only debug 1 is even trying to be nice, telling you this is an automatic command that ret is used as a jump to next. Okay, so and as you can see, not exactly the same text. So what happened? Still no one sees? No. So basically, here you have a 66 prefix on return, which actually makes return return to IP and not EIP. So actually, you don't jump to 401.008, but to 1008. And in this proof of concept, I mapped the null page and I did some code at this address. So this is actually not a return to this. And another problem is that officially this is also called a return. It's not. So all the disassemblers added their own way of disassembling it, like small return or return 16 or something like this. But actually, officially, it's the same mnemonic. So that's the latest hue, I think, and that's only debug 1. Now I think maybe the latest only debug 2 fixed that, but you can still be tricked just by that. And this 66, so the jump to EIP also works on calls, returns, loops, so all the flow control opcodes. So I won't enumerate all the tricks because otherwise you'll die of boredom probably. And if you want more, then I created a page on Corkami, and I already made some graphs and cheat sheets to have an easy list of opcodes. And it's quite too much theory for now, so I don't like just reading stuff and not having something to feed my debugger. So I created COST, which stands for Corkami Standard Test. COST is a single binary. It's just running. There's no option. You just run it, and it will just execute a lot of different tests. And then I also made it hardened P, so it may be it may also help you to test the P sides of your tools or your knowledge. But because in hardened P it's actually quite difficult to debug, I also made an easy P mode so that it's you can study only the assembly and not have too much trouble debugging it. So COST contains a lot of tests. I still have some time. Yeah. cost contains a lot of tests, classic stuff, so very trivial stuff, then a few more complex stuffs like jump to IP, IRET, undocumented opcodes, CPU specific like MoveB, pop count, CRC32. Also some detection of OS and VM by using common opcodes like what was the name? The blue pill, no, the red pill trick. Yeah, just SLDT execution, and you get a value and you compare, but it's the blue pill or whatever. And also some OS bugs, because sometimes Windows XP was doing wrong job trying to tell you which was the exception that just happened. And it would be a way to make the difference between the actual OS and the emulator that would try to be logic. Export cost is written in assembly, so there's no extra, it's not compiled and it's not generated. But to make it self-documented, I created internal export so that each section of the file is easy to browse, so that you will know what, if you would quickly want to jump to the 64 bytes part and everything, then it's easier via the export. And also I wanted it to print a message in the most convenient way. So, but if you keep printing a message, then it will make the assembly wider, I mean longer to scroll. So I use the vector exception handling, and a fake opcode, so that you have the comments of what's going to happen appearing directly in the code. So it's a kind of self-documented, without debug symbol file. And as you saw, it doesn't have much of output, but actually it has a lot of debug outputs, like 100, I forgot message, and it's even saying trick, I'm going to do this, and then I'm going to do that. So trying to make it helpful, yet a bit hard to disassemble. Can anyone understand what this code is doing? This is one of my favorite. Yeah, that's not trick this time. This is not a.
It was critical last time.
Yeah, sir. Yeah, sorry. So basically, you push some arguments on the stack and you jump to here. So basically, with the return file, you will jump. So I push the EIP on the stack with a 33 word. So basically, I will be returning far to this. So basically, I will return back to this EIP in the selector 33. If this is in a 64-bit OS and this is a 32-bit process, you will return back to execution here in 64-bit mode, because selector 33 is the selector for 64-bit mode, which you can access from a 32-bit process. So basically, this code will be executed first in the current selector with, so as you would see, and then it's executed back on selector 33, which means in 64-bit mode. So you have the same EIP, you have the same opcodes, but the disassembly will be different, and I chose some opcodes that would make mnemonics specific to each size, 32 bits or 64-bit size. So it's already quite a bit to disassemble, because same EIP, so unless you're careful about the selector, well, it's a problem. And I think the APIs, Windows debugging APIs, are just enabled to make you step through that. It's a problem of the API, not a problem of IDA or WinDBG itself. So basically, you can't debug that code in 64-bit mode. And you could do that if you just, but if you run over it after you return to the original selector, which is why there is the push CS here, and you go back to end with the original selector, execution will go through quickly, but you cannot step through that code. So killing disassemblers and debuggers, and yet simple. So here is the result that you get when you run cost with the latest, the latest public version of Hue. I think it's going to be fixed. So this is a hint knob that's not documented by Intel, and it's a bit forgotten by most disassemblers. So WinDBG and Hue are giving you undocumented question marks, or the Hue style of question marks. Then, since that was originally what I planned to present hash days, but then I decided to bring a few tricks in the cost itself on the P side of things. So this is the header. So it has MZ and then it's some text. So you can type cost and it has some text. I made it typable, and the NT headers the P headers, the one starting with P, is actually at the bottom of the file. The bottom of the file is here, so it's a footer. And I made it so that the values are quite critical. I mean, so they are not the one you would expect. So this is the result that you would get when you were loading a cost under IDA 6.1. So yeah, some values were random and everything. But if you just have, with cost you can test, you can set the values of a register and then compare it, but you cannot test all the possibilities of PE files with a single file because you have to choose. So for example, cost has no section, it has weird alignments and everything, but you cannot make all the possible case. So I went on and I created another page on Corkami with, as usual, the proof of concept, some graphs about PE files and everything. So I don't consider it finished, but I consider good enough to break a bit everything. And I already created more than 100 proof of concept, which try zero section, big alignments, huge alignments, and I have some funny results. So here is the virtual section table versus hue. So when you're on low alignments, you can have no sections, or the section table can be empty. So basically, I made the size of optional header point in virtual memory space, which means the section table is out of the PE file. And Hue doesn't like this, and the consequence of that is that it doesn't even think it's a PE file when it's fully working, but this trick only works under XP because Windows 7 is a bit more picky on the unused section table values. So when you got some ASCII art in the data directories, then you can probably guess that there's something going on. If you have better ASCII art suggestion, all ears. So basically, this is the dual PE header that was presented by Reversing Labs in Black Hat. So you are familiar with that? No? Yes? So basically, you extend the size of headers so that the headers will, the empty headers will be actually mapped at the bottom of the file, so that when it's so that it's far enough to reach section alignment, and when you load that in memory, the first section will actually be mapped over it. On the top, the first part of the optional header is the one used on disk. So this is what is used to check if the file will load, but the data directories are read from the values in memory. So first, the optional header is parsed, is mapped in memory, then the section is folding itself over the bottom part of the header, and then the true data directories that were originally at the start of the section will be taken into account. So all this is garbage and is visible on disk. It follows the size of optional header, but actually in memory, this is not what is used to be parsed. Another weird thing is that the export names can just be absolutely anything until a null character, which means non-ASCII, whatever. And the problem, another funny thing is that Hue displays them inline, so you can just add your own adds because those are just export names. And one of those export is actually more than 60K, so that it's good enough to create a buffer overflow if your tool is not careful about that. And it's also possible to have a null export, like just a character null, and you can import a null API. It's no problem. I also, just trying to see the different possibilities, I created a few files that had the maximum number of sections. The limit is 96 under XP, but it's 64K under Vista and 7, which means, well, Oli debug 2, the latest Oli debug gives you a funny message, but it still loads the file. Oli debug 1 crashes directly on this file. Still some time. And the one last, not very visual, but I noticed that the address of index of the TLS is overwritten on loading, and imports, the terminator of imports doesn't need to be 5 null D word, but only if the name is 0, then the descriptor, the import descriptor is considered the terminator. And so basically, if you make address of index point to the name of an import descriptor, you could get that overwritten, and then the imports will be truncated, will be considered truncated. And actually, the behavior is different under XP or Windows 7. So under XP, it's overwritten before, after imports loading. So the whole import table is not truncated, while on Windows 7, it's happening before the imports are loaded, which means you have the same P, but different loading behavior under different version of Windows. And the file works on both versions of Windows. Oh yeah, sorry, before that, maybe I still have some time. How long do I have? So 15 minutes late? Okay, sorry, I'll do the demo. I'll go through the, okay, so this is just to prove, sorry? Sorry?
You have time.
Oh, okay. Yeah. Yeah, that's how I understood, yeah, sorry. So, just to show you how the kind of, resizing. So this is the kind of PE files that I typically create. So I only define the elements that just need to work, and this is actually a driver. So even though I use some undocumented opcodes. It's a working driver, and it doesn't have the usual stuff you have in the driver. So you can this just to say that this is a kind of proof of concept, clear to see. You don't have external stuff that bugs your view or your debugging. So this is this one is just to see the possible values of CR0s via the SMSW, which is theoretically undefined on higher words, but it actually gives you the same value as the standard move EXCR0. And here is move EXCR0 with the wrong mod RM, which in the latest hue is actually incorrectly, well, not disassembled at all. And so if you just, sorry, whoops. Let's hope it doesn't crash. Oops. So as you can see, you get exactly the same value whether you're using the normal CR0, the invalid one, and the undefined. So the upper part is supposed to be undefined. Usually when it's undefined, it's zeros in Intel language, but here it just works fine. And my machine didn't even crash, which means the driver is fine. So you can study small drivers. The first proof of concept that I presented here was the one with all the disassembly. So anyone still knows what the value is? So basically, some opcodes are here for garbage, just to prove that they are actually they are just used as junk. But still, the registers are actually modified, and these opcodes from the 70s or something, or just the early 80s, are still perfectly working on a modern CPU or even i7. One of the proof of concept I created is the one that actually tests the values, the initial values, so that you can see what would be the possible values, whether it's on XP or Windows 7. So each time I just save all the values of the registers, and then I compare them to possible values. So I test them one after each other. Actually, on TLS, you have much more control of the values, because the values you will get in the TLS unloading in the TLS are the TLS RVA, the callbacks, the size of the TLS. You get that in EB. Well, I forgot exactly, but it's in the source. So you can get running this will help you to actually mimic an emulator better, if you an OS better in your emulator, if that's what you're interested. So SMSW is actually the one comparing. So the one using SMSW, then comparing the value, and then checking whether the register changed, and then when it reverts normally. A funny fact that I would like an explanation if you know it, is that actually the behavior of this file is different if you run the file normally or if you run it with a redirection. So if you pipe the output, you get a fail result, and if you run the file normally, it just works. So here I will just run it, and then I will run it to a file, and then just type the result. And oops, normal execution, okay. Redirection, fail. If you guys have any explanation for that, I'm all ears.
Does that work with files or with device output as well? Like from one to
Oh, I didn't try that. Just so you would pipe to another device, and yeah, but then how you get back to printer? Or yeah, I don't have a COM device or. Yeah, I don't know. I don't know. Yeah, but there was a big surprise because I had a test bench and then fail, and then run. Okay, so okay, I have no idea why. The GS trick, quite simple, and I also have some outputs. So I modified JS, then I reset and waited for result, and then I'm doing 2 resets and checking the time between, so that it shouldn't happen too quickly. Nops. So so I'm testing the undocumented knobs. I'm testing the knobs that are on invalid page, and I'm testing the. Sorry, I will actually debug it. So standard knobs. (32-bit mode), then the knob on. Oh yeah, sorry. Now I can't do it because I don't have 64-bit mode. Yeah, that's why. So all my 64-bit tests are still done in 32-bit process, so that you can run them on a normal OS, and then it detects by JS if there is 64-bit available, and in this case you will get a different result. So if you run it on 64-bit, which I don't have here, you will actually get the actual test on 64-bit and the results printed out. But still, it's not possible to actually debug that easily. But it's at least there is no trick over there, so it's easy to bring back to a 64-bit process. Push ret. So here you print the output, and then only nicely tells you that you will jump to 4008, but actually here the display actually is correct here. It will actually return here, and the TLS already created the null page, which prints fail. So it's as expected, but there's no standard way to disassemble that correctly. I can't execute the working 64K section, and actually I'm executing all the code. So I'm just starting at the beginning. The sections are quite big, and I'm modifying EAX so that all the zeros are executed. And just to do a printf in the end, it actually takes a few seconds to execute on the i7. So it's quite funny to see you launch it, even when the cache is loaded and the OS is ready to be fast. You launch it, and printf comes a few seconds later. So virtual section is the one that Hugh doesn't think it's a P at all. So this is the latest Hugh. Well, it's been patched anyway, but just because, yeah, well, I can't browse P on Hugh now that that it doesn't think it's a P file, but basically it thinks that the optional header points to the end of the file, beyond the end of the file. The folded header, oh yeah, a few error messages because of the wrong data directories, and the actual data directories at the start. At the start of the section. So this will be the imports and the actual real data directories. And last, the one with the TLS address of index that is pointing. Oops. That is pointing inside the imports at the address of name. So it will override the loading, and when you just load it, it just says, oh, it's XP because my imports were loaded this way and not the other. And if you run that file, it will give you another reason. And then the exports, where some of the exports are actually very long, and you have kind of you can see that actually here I'm even taking over the disassembly, so I'm just repeating the same fake opcodes and address, so you could actually fool the disassembler that way. I think it's just a visual effect. There are no big problems, but it's a known problem that was fixed recently in IDA, that if you put an export in the middle of the instruction, then the fake export would actually take over the disassembly, and then that would ruin the disassembly. there's actually a proof of concept for that in Core Kami, of course. So that's all for the demos. Oops. So I wanted to know more about x86 and PE, which are far from perfectly documented and are still not perfectly documented, but at least I've been covering some parts of it. There are still some gray areas, but at least every day I'm just learning a bit more and publishing my results and sharing them openly. Like WinDBG, if you will actually follow only the official documentations, you will only get bad results with malwares and packers out there. So if you yourself are interested, or you develop a tool, an emulator, an engine, or whatever, well, you can just visit Core Kami, read the page, and download all the proof of concept which are available. And if you find any bugs, which might happen, then send me a postcard or send me a Red Cross t-shirt. So thanks to Peter Ferry and all my reviewers and people who contributed. Do you have any questions?
Did you, like for your PE format tests, did you run them through AEs?
No.
And the virus scanners?
No.
You will find a shitload of everything.
Yeah, but I'm not. Then I wouldn't be good to actually turn them into exploitation or anything. So I don't know. Yeah, but already breaking all the disassemblers and stuff was good enough. I found a crash in Intel Z, which was good enough.
And other people have fun with it.
Any other question? Everybody survived the presentation?
Great talk, man.
Hmm?
Great talk.
Thank you. So thank you.